In today's lecture, we are going to discuss about continuous functions and its properties. So first of all, we have to understand analytically what does it mean to say a function is continuous. Intuitively, all of us know what it means, a continuous function. For example, suppose I look at a function whose definition is where a and b, these are two real numbers. Depending on a and b, if I want to draw the graph of the function f, it will look something like this. Well, this looks really continuous, that there is no gap in the function. One can draw it continuously. This is the intuitive feeling, which we want to make analytic in terms of the language of mathematics. But first, again, let's try to examine what does it mean to say a function is not continuous. Okay? Again, intuitively we know what it means. Let's try to draw a function whose graph is not continuous. It should look something like this, that suppose I have a point here which I call x0, and the graph of the function looks something like this up to x0, and just after x0 it starts from here. Okay, you see just at x0 there is a big jump. Well, this is certainly example of a function which is not continuous. But again, in terms of analysis, let's try to see what it means. Well, this height, if I draw it here, this is f of x0 here. Okay? Then what does it say? It says that if I look at this kind of a neighboring points, let me call this point fx0 plus epsilon, and let us call this point f of x0 minus epsilon. Then if I look at neighboring points of x0, whatever neighboring points I look at, okay, let me call them x0 minus delta, x0 plus delta, I see that if I take points from this region, it is not true that f of x lies in this band. You see what is happening here. If I take a point here, then the height of the function is this, which is going out of fx0 plus epsilon. Okay, this is the property which we are going to exploit in defining what is a continuous function. So let us just try to write down what have we got for this example of function which is discontinuous according to our intuition. Okay, what we got is as follows, that there exists an epsilon bigger than 0 such that for all delta bigger than 0, mod of x minus x0 less than delta does not imply mod of fx minus fx0 is less than epsilon. Written in other language, there exists an epsilon bigger than 0 such that for all x satisfying x in the interval x0 minus delta, x0 plus delta, it is not true that fx belongs to fx0 minus epsilon fx naught plus epsilon. According to our pictorial analysis, it just says that there is some gap in the graph of f. And when I say a function is continuous at a point x naught, this is precisely the thing which I don't want to happen. Then what should be the definition of continuity of a function? If I don't want this or this to happen, I don't want this to happen. So I define continuity of a function at a point x naught in the following way. Let f be a function from R to R. Let x naught be a real number. F is called continuous at x naught if given any epsilon bigger than 0, there exists a delta bigger than 0 such that whenever modulus of x minus x naught is less than delta, then modulus of fx minus fx naught is less than epsilon. In other words, if x is in the interval x naught minus delta and x naught plus delta, then fx belongs to fx naught minus epsilon and fx naught plus epsilon. Notice who depends on what. I start with an epsilon. Always remember the example of the discontinuous function which I said. There what has been said is I can always find an epsilon for which no delta works. If I don't want this to happen, I have to look at the opposite statement of that, which should mean that whatever epsilon you take, there is at least one delta which works. Which works means, in this language, that if x is in this interval, then fx belongs to this interval. Well, this is definition of continuity. But if I want to claim that this is definition of continuity, what I should do is, the functions which I intuitively know are continuous functions, I should be able to verify that those functions are also continuous with respect to this definition. Any mathematical definition should match with the intuitive feeling we have, right? So let's check now. So I start back with the function which I started with. Let us take the function fx equals to ax plus b. And let's try to check the continuity of this function at the point, let us say, 2. So my claim is f is continuous at x equals to 2. And once I do the proof, you will be able to see that the same proof works for any other value of x. 2 is just a particular case. It is nothing, there is nothing holy about 2. Okay? So what I have to do? I have to choose an epsilon. Can I take epsilon to be equals to 1 and find a delta and show that the condition of continuity is verified? Will it work? I say no, because the definition says it has to work for any arbitrary epsilon. That means I cannot assign a value to epsilon. I just have to start with an arbitrary epsilon, and out of that epsilon I have to find out a delta. Okay? So choose epsilon bigger than 0. Okay, I cannot specify the value of epsilon because epsilon is arbitrary, right? Now I have to find a delta. So to find delta bigger than 0 such that if mod of x minus 2 is less delta, then mod of fx minus f2 is less epsilon. Now what I know is, I know the explicit value of f. I know what f is. So I will put the value of f in this equation, which I call star. Well, it's not quite an equation, sorry, it's an inequation. So this then looks like modulus of ax plus b minus 2a minus b. So I have to prove that this is less than epsilon. Okay? Now let's try to estimate, look at this quantity. First of all, what you get is that this b cancels each other. So what you are left with is mod a times mod x minus 2 is less than epsilon. Still my job is waiting me. I have to find a delta. What is delta? Well, then this implies that mod x minus 2 is less than epsilon by mod a. Now just check. Suppose I choose, suppose delta is equals to epsilon by mod a. Suppose I choose delta to be this. Then what happens? Well, I again look at mod of fx minus f2. The condition I am taking is modulus of x minus 2 is less than epsilon by mod a, because this is my delta. And now I want to check whether modulus of fx minus f2 is less than epsilon. This is what I want to estimate. So if I again write it down, you will see that I just have to work backward. The way I got delta, now I will try to go just in the reverse direction, which is easy, because this quantity is just modulus of ax minus 2a, which is mod a times mod of x minus 2. But mod of x minus 2, I already know that this is less than epsilon by mod a. So this quantity now is less than mod a into epsilon by mod a, which is equal to epsilon. And this is precisely what I wanted to prove. I got a delta, my value of delta is epsilon by mod a, and if mod of x minus 2 is less than this delta, I can prove that mod of fx minus f2 is less than epsilon. Let's look at another example, which is slightly more complicated than this. Let us look at the function fx equals to x square. Okay. Well, if you think about the graph of this function, many of you might have seen the graph of this function. It looks like this on the positive axis. At 0, obviously the function is 0, and as x grows, as x increases, the value of x square also increases. It gets larger and larger. Okay. The graph of the function, they will look like well, there is something involved here. You might actually ask me that how do I know that the graph of the function curves the way I have written it? It is not the other way. Well, for that you have to wait a bit. But believe me, for the time being, that the graph of the function on the positive axis actually looks like this. Okay? So it looks certainly continuous, because I don't see any gap. So I will like to check analytically again through my definition that how does continuity gets verified, let us say for x equals to 1. So let's choose the point x naught equal to 1. And I have to check continuity of the function at the point x naught equals to 1. So again what I have to do, I have to start with an epsilon bigger than 0. And then I have to find a delta bigger than 0. So choose epsilon bigger than 0. And then I look at the quotient, the difference, f of x minus f of 1. How does this look like? This is then modulus of x square minus 1. So this is then modulus of x minus 1 into modulus of x plus 1. Okay, and now I want that this quantity should be less than epsilon. So want to find a delta bigger than 0 such that notice that delta is in my hand. I will choose it according to my will. Okay. Now, which delta should work? I say first I need to concentrate on this quantity. If I can somehow choose x such that mod of x plus 1 is less or equals to m, I choose only those x's, then it will turn out that modulus of fx minus f1 is less or equals to m times mod x minus 1. Okay, and I want to make this less than epsilon. Now let me make this m specific. What I will do is I will choose x in 0, 2. Then mod x is anyway less than 2 and mod of x plus 1 is less than or equals to 3. This implies that if I choose delta to be equal to minimum of epsilon by 3 and 1, let us see whether this works. Okay, this choice of delta. So let us take an x such that mod of x minus 1 is less than delta, which is less than 1. Okay, delta is less than both these quantities. Fantastic. Now if mod of x minus 1 is less than 1, that means the distance between x and 1 is at the most 1. This implies in particular x belongs to the interval 0, 2. Correct? Now let's try to estimate fx minus f of 1, which is by definition x square minus 1. I write it as x minus 1 x plus 1, which is less or equals to mod x minus 1 into mod x plus 1, but mod x is anyway less than or equals to 2, so this is less or equals to mod of x minus 1 into 3. But mod of x minus 1 is less than epsilon by 3 also, so this is less than epsilon by 3 into 3, which is equals to epsilon. So you see that this delta works. I am not claiming that this is the only delta works. You can actually see from this example very easily that if you choose any other delta 1 which is less than this delta which I have chosen, again you will be able to prove that mod of fx minus f1 is less than epsilon. But what is important to notice here is that the definition of the description of delta, that explicitly depends on the epsilon which you are starting with, and it also has something to do with the value of the function also, the way the function has been defined. You see, this epsilon by 3 has come because of the factorization which I am using. At the same time, the value of delta is also depending on epsilon. That means if you change your epsilon, your delta will also change. But then there is nothing wrong in that, because according to the definition of continuity, we just said that given an epsilon, there is a delta. Nobody prohibits delta from depending on epsilon. Now, although this definition of epsilon and delta is mathematically extremely rigorous, but for many practical purpose, given the nature of the function, sometimes it becomes difficult to apply this epsilon delta definition to check continuity of the function at a point. For that reason, we want to manufacture some other procedure by which perhaps we can check continuity of a function much more easily. And this actually brings us back to something which we have already discussed, the sequences. So what I'm going to describe now is to connect the concept of continuity with convergence of sequences. So this is how we start. And what I want to prove is as follows. So let me write it as a proposition. Let f from R to R be a continuous function. If xn, which is a sequence of real numbers, converges to x naught, then if I look at the sequence f of xn, which makes sense, because xn's are just points, I apply f on those points, I get another sequence of numbers which is fxn. Then this fxn converges to the number f of x naught. Conversely, if f is a function from R to R and for every sequence xn converging to x naught, the sequence fxn converges to fx naught, then f is continuous at x naught. This actually clears the concept that if you want to check continuity of a function at a point, let us say x naught, all you have to do, take any arbitrary sequence xn converging to x naught, just check whether f of xn converges to f of x naught. What is the advantage of this? First of all, we have seen mechanisms of finding limits of sequences, right? Sandwich theorem and many such things. You can use those weapons to prove convergence of f of xn, and once you know f, you will anyway know what is f of x naught. So using the concept of limit of a sequence, you can actually check continuity of a function at a point. That is, in some way, you are bypassing the concept of epsilon and delta. But once I prove this proposition, that will actually connect that these two are equivalent. That's why the theorem is actually in both directions. So first, let's try to prove the first part. So I assume that f is continuous at x naught. I choose a sequence xn which converges to x naught. To prove that the sequence f of xn converges to f of x naught. So for that, you know what I have to do. Again, I have to start with an epsilon. I have to find a stage after which the distance between f of x naught and all f of xn's after a stage, the distance is less than epsilon. So choose epsilon bigger than 0. Now since I have assumed that f is continuous at x naught, given this epsilon, there is a delta. So there exists a delta bigger than 0 such that mod of x minus x naught less delta implies mod of fx minus fx naught is less than epsilon. Notice my assumption is that xn is a sequence which converges to x naught. That means given this delta, there exists a stage after which modulus of xn minus x naught is less than delta as xn is converging to x naught. So there exists a capital N such that for all n bigger than or equals to capital N, modulus of xn minus x naught is less than delta. Now for the first time actually I am using continuity of the function. This implies modulus of f of xn minus f of x naught is less than epsilon as f is continuous. But is not it the convergence of the sequence f of xn to f of x naught? See, given epsilon, this is the epsilon which I started with, I found a stage capital N such that for all n bigger than or equals to capital N, this is happening. And this is what I wanted to prove. This implies convergence of the sequence f of xn to f of x naught. Well, now it is the other way. So what is my assumption? Now the converse part. What is my assumption now? Assumption is if xn converges to x naught, then f of xn converges to f of x naught. I have to prove f is continuous. That means what? Given epsilon, I have to find a delta. Now here the complication starts. Directly if you approach, it becomes difficult to prove it. So what we do is, we use the contrapositive argument, which we have used earlier, you must have noticed. What I do is, I will assume that f is not continuous at x naught. And that assumption I will use to contradict the assumption which I have started with. That means my assumption is actually wrong. And hence it will follow that f must be continuous at x naught. Okay? So assume that f is not continuous at x naught. Well, if you go back to the first thing which we have discussed in the lecture, that what does it mean to say a function is not continuous at a point? I am going to exploit that. It means that there exists an epsilon for which no delta works. Okay? That means whatever delta you choose, modulus of x minus x naught is less than delta, but modulus of fx minus fx naught is bigger than epsilon. Okay? So there exists epsilon bigger than 0 such that mod xn minus x naught less than 1 by n does not imply is less than epsilon. That is, in other words, so how come suddenly I get this xn? Well, the definition says there exists an epsilon for which no delta works. What does it mean to say no delta works? It means there exists an x such that modulus of x minus x naught is less than delta, but modulus of fx minus fx naught is bigger than epsilon. There exists an x, keep track of that. That x I am actually calling xn because I am choosing my delta to be equals to 1 by n. Corresponding to this delta, there exists an x which I am calling this xn. Okay, so this is how I get a sequence at least. And notice that the sequence xn converges to x naught. Okay, this implies xn converges to x naught. But then by my assumption, this implies f of xn converges to f of x naught. But notice that what I got here, that f of xn minus f of x naught is bigger than or equal to epsilon. Then how come this happens that f of xn converges to f of x naught? Because this is true for all n. And if a sequence has to converge somewhere, then after some stage their difference has to become as small as I wish. But that is not happening. It is always bigger than the epsilon, and this is a contradiction. This is a contradiction. And this implies that the assumption I started with, that f is not continuous at x naught, is actually wrong. This implies that f is continuous at x naught. And this is what we wanted to prove. Now let us try to see how to exploit this sequential criteria of continuity to show certain functions are continuous. Okay. So I will start with the functions which I have already dealt with. So what I will do is I will use this sequential criteria to again show you that those functions are really continuous. Okay. So let us start with this example, and you will see in this case proof is much easier. We start with the function fx equals to ax plus b. I want to prove that f is continuous at x equals to 2. So how do I proceed through this sequential criteria? I just choose any sequence xn which converges to 2. Now if you remember your lessons on sequence, that if a sequence xn converges to L, then any scalar times xn converges to the scalar times L. If xn converges to L, yn converges to m, then xn plus yn converges to L plus m, so on and so forth. I am going to use all those properties. Now I say that this implies that a times xn converges to a times 2. This again implies that a times xn plus b converges to a times 2 plus b. Here I am taking b as a constant sequence. But if you notice clearly that this quantity is nothing but f of xn, and this quantity is nothing but f of 2. So I have shown that f of xn converges to f of t. That means f is continuous at x equals to 2. Now let us look at the second example we looked at. Say fx equals to x square, and I am checking continuity at x equal to 1. So how should I proceed? Start with the sequence xn which converges to 1. But then this implies that xn times xn, which is xn square, converges to 1 times 1, which is 1. And then this quantity is nothing but f of xn, and this is nothing but f of 1. And that is what I wanted to prove. If xn converges to 1, f of xn is converging to f of 1. This implies f is continuous at 1. See how simpler the proofs are. Now I will show you that certain other functions which usually looks more complicated in terms of epsilon and delta can actually be dealt with the sequences quite easily. For example, let us look at this function. F of x equals to sine of 1 over x, where I choose x to be bigger than 0. And I define it to be equal to 0 if x is equal to 0. So I define the function fx equals to sine of 1 by x when x is not equal to 0. And I define it to be 0 if x is equal to 0. And I want to check the continuity property of the function at x equal to 0. So want to check continuity of f at x equal to 0. So what I do is, I have to choose sequences. So let me choose this sequence first. Xn equals to 1 by n pi. N equals to 1, 2. Notice then that Xn converges to 0. But then what happens to f of Xn? That turns out to be sine of 1 by n pi, which is sine n pi, which is 0. So this implies f of xn converges to 0. But does this prove continuity of the function at x equal to 0? I say it does not, because what I have shown is there is a particular choice of a sequence xn for which f of xn is converging to f of 0. But the definition says for any arbitrary sequence xn, f of xn should converge to f of 0. Okay? Now let's look at some other sequence and see what happens. Let me choose this sequence now, which I am going to call yn. This is 1 by twice n pi plus pi by 2. Notice that yn converges to 0 as n goes to infinity. But then what is f of yn? That is sine of 1 over 2n pi plus pi by 2, which is just sine of twice n pi plus pi by 2. But all of us know that sine of 2n pi plus theta is sine theta. So this is sine pi by 2, which is equals to 1. And this is not f of 0. That means the function is not continuous at 0. Because if it were, then for any sequence xn converging to 0, f of xn should converge to f of 0. But that is not happening. I have found a sequence yn which converges to 0, but f of yn does not converge to f of 0. Well, you might say that it is my fault. I have defined f0 to be equal to 0. That's why it is not happening. Can I define f at 0 in such a way that it will become continuous? Well, these two choices of sequence actually tells that it is not possible. Whatever value of f0 you give, these two sequences are always there for which f of xn will converge to either 1 or 0. That means you cannot choose a value of f0 where for all sequence f of xn will converge to that value. It is not possible. So this implies f is not continuous at x equal to 0. Let's look at the fourth example where I am just going to do some little bit of plastic surgery with the function which I have already taken. So let me define now fx equals to x sine 1 over x when x is not equal to 0. I define it to be equal to 0 when x is equal to 0. And I want to check whether this function is continuous at x equal to 0. So I take a sequence xn which converges to 0. To check that f of xn converges to f of 0 which is 0. I have to show whether this is true or false. If it is true, then f is continuous. If it is not, then f is not continuous. Now notice that as xn converges to 0 and sine of 1 by xn is actually a bounded function. So I want to prove that xn sine 1 by xn actually converges to 0. So to prove that xn sine 1 over xn converges to 0. Once I prove this would imply that f is continuous at x equal to 0. Okay? Now to prove this, I can just apply the definition of convergence of a sequence if I like. Start with an epsilon bigger than 0. Then there exists capital N such that mod of xn is less than epsilon for all n bigger than or equals to capital N, because I have assumed that xn converges to 0. But then what do I know about xn sine 1 by xn, where n is bigger than or equal to capital N? I know that this quantity is less than or equals to modulus of xn as mod sine y is less or equal to 1 for all y in R. And modulus of xn is anywhere less than epsilon. That is what I have written here. So this implies f is continuous at 0. So this is how actually one uses the sequential criteria to check continuity of a function or even discontinuity of a function. Now, using this sequential criteria, it becomes possible to construct more and more examples of continuous functions. Okay? So this is how we proceed. So I just write it as a theorem. If you have gone through all the results of the sequence which I taught you, you will be able to prove all these results quite easily. So the first result is, if f, g are continuous at x naught, then so is f plus g. What do I mean by f plus g? It is another function whose definition is f plus g at x is fx plus gx. I can also prove that if f and g are continuous at x naught, then so is f dot g. What is f dot g? F dot g is another function whose definition at x is fx times gx. Similarly, if g of x naught is not equal to 0, then f divided by g is continuous at x naught. But here in this third problem, there is something which bothers us, that can it happen that g is continuous at x naught, g is non-zero at x naught, but in every neighborhood of x naught g is 0. Can that happen? Intuitively you feel it cannot happen, because then there is a jump. G of x naught is either positive or negative, then in every neighborhood if g is 0, then we are in trouble. So to understand that 3 is really true, if you want to feel it, you should solve the following exercise. It follows just by following the epsilon delta definition of continuity, that if a function f is continuous at 0, then, well, sorry, let me change it. If it is continuous at a point x naught, let us say, and f of x naught is not equal to 0, then there exists a delta bigger than 0 such that for all x in an interval around x naught of length 2 delta, which I will write as x naught minus delta, x naught plus delta, it happens that f of x is also not equal to 0. What actually it illustrates is the following picture, that this is your point x naught, and f is non-zero at x naught, means it is either here or it is below. Suppose it is here, then the graph of the function has to look like, it cannot happen that the graph of the function looks like this, and it is 0 here, 0 here. That is quite obvious, because this is the jump which we wanted to avoid in our definition of continuity, you see. So what I am asking you is to prove using the definition of continuity that this kind of situation does not happen. Now just let us test our understanding. We ask the following question. See, if you look at this picture which I have drawn, that at this point x naught f is continuous, but you see in the picture what is happening is, in the neighboring points of x naught also f is continuous, because the graph is continuous. Is it generally true that if a function is continuous at a point, then it is continuous in some neighborhood of that point also? So that is the question I want to ask now. So question is, if f is continuous at x naught, is it true that there exists delta bigger than 0 such that for all x in x naught minus delta, x naught plus delta, the function f is continuous at all x. That means, is it true that f is continuous in all the neighboring points? Okay. If you think a little bit, you will see it is very difficult to imagine such kind of a function whose graph you can really draw. But if we test analytically, I am going to show you that some such functions exist where it is continuous exactly at one point and nowhere else. So the example is this. Let us define this function f(x) equal to 0 if x is rational and equal to x if x is irrational. First, let us check where f is continuous. I say f is continuous at 0. How? Well, I choose a sequence xn which converges to 0, and notice that f of xn is always lesser equals to mod of xn. This implies f of xn converges to 0. But this is nothing but f of 0. That means f is continuous at 0 at least. But what happens to other points? Let us take a point x naught which is not equal to 0. And then I take a sequence of rationals Rn converging to x naught, where Rn rational. And I take a sequence In which are irrationals which converge to x naught. Then what happens to f of Rn? By definition, f of Rn is equal to 0 for all n. This implies that f of Rn converges to 0. But what about f of In? By definition, this is In which converges to x naught. This implies if x naught is not equal to 0, then f of Rn, the limit is not equal to, but this cannot happen if f is continuous. If f is continuous at x naught and xn converges to x naught, f of xn converges to f of x naught. That means in particular it is meant whatever sequence xn you take which converges to x naught, all the f of xn's has the same limit, which is not the case here. I get a difference. Implies f is not continuous at x naught. What is interesting about this function is, you might have thought that why we are asking for this analytical definition of continuity. Because intuitively we can feel what continuity means, that you can draw the graph of the function without taking the pencil out of the page. The point is, for every function, you may not be able to draw the graph of the function. And this is one function whose example I have given. You cannot actually draw the graph of the function. So you need some other tools to describe continuity of a function. And that is what is the analytical description of the continuity which we were discussing. In the next lecture, we will discuss more about the deeper properties of continuous functions.